Okay, so just as a refreshment, so last lecture we talked about coordination compound, and so just remember that a criteria for forming a coordination bond, or what we call a dative covalent bond, is that you must have lone pairs on your ligands. Okay, so the picture that I found online when we have a coordination bond is where your metal ion has an empty orbital, where it acts as Lewis acid to accept a pair of electrons from the ligands. As you can see in this case, we have ammonia, and we know on the nitrogen there's lone pair, and then it can be donated where the metal and the ligand start sharing these two extra electrons, forming this coordination bond. And there are two types of ways to treat these bonds. For the classic inorganic, we treat these bonds as pure electrostatic interaction. Okay, so I know it may seem a little bit confusing. The way you think of it, you can recall the acid-base reaction where your proton, H plus, doesn't have any extra electron, and then when your base, they have extra electrons, and it's kind of donated to that hydrogen and forming a covalent bond. Okay, so we can do the treatment and calling it there electrostatic. And the last time we talked about valence bond theory, okay, and then we'll refresh on that in a little bit. Okay, so basically valence bond theory does not really explain the spectra and magnetic properties, so you must use crystal field theory in order to explain the color and the magnetism of your coordination compound. But valence bond theory explains the geometry. And the ligand field theory, you will see that in inorganic chemistry, where it will actually utilize molecular orbital to explain in depth of what's happening. Okay, so briefly on valence bond theory, so the geometry of your complex is really depending on your metal ion or orbital hybridization with the ligand that you have. And last time, if you look at your textbook on page 1055, so you can see because there's extra d orbitals, these transition metal are capable of accepting electrons from the ligand. And depending on which orbitals are used, the geometry can be varied. For example, for the most common coordination compound geometry is octahedral, which means you have 4 ligand on the same plane with 2 ligand, one on top and one on the bottom, forming this 6 coordination number compound. Okay, so if you are using D2sp3, that gives you octahedral. And similarly, when you have a 4 coordination compound where it utilizes dsp2, it will give you a square planar structure, and this is very common for D8 metal ion. So what I mean by D8 would be if you draw the electron configuration, you have 8 electrons in your d orbitals. All right, so and then for the sp3, I mean we already learned that for mostly carbon type of containing compound, you would have a tetrahedral structure. But in the case of inorganic compound, generally the D10, such as the zinc +2, would adopt such structure. Okay, so you're using the sp, is a hybridization based on the s orbital and p orbitals. So as we get to the crystal field theory, it's assuming the interaction between the metal cation and the ligand are electrostatic. Okay, so metal cation is positive charge and your ligand are negative charge. Okay, I know it sounds confusing for ammonia and phosphine type of ligand, but you can think of it where it's electron rich, that's negative charge. You have electron deficient, that's positive charge. Okay, so for free metal ion, as you see on the left, the orbitals are equally distributed. And for these d orbitals, there's multiple type of d orbital because we know each orbital can hold 2 electrons, right? And for d orbital, a typical metal ion will have 10 of them, okay? Even though they're not using all of them, but it's there. An orbital is where we're likely to find electrons. Okay, so there are several types of electrons, so where you have two scenarios. For the dz squared and x squared minus y squared, those are directly in the same direction as where your ligand would be. Okay, so if you imagine you have ligand at all these places, so the dz2, z2, that means on the dz direction, you have two of those orbitals. And then for the dx squared minus y squared, that's on the xy position, you have two of those orbitals. Okay, so they are directly interacting or responsible for explaining the ligand to metal interaction. There's also a possibility that you can find these electrons in between these two ligands, okay, because the electrons are just running around, right? We really don't know where they are, okay? So for the dxy, dyz, it's just the orbital exists between 2 points, okay? So you have dxy, dyz, and dxz. This just simply tells you which coordinate we're looking at, okay? So since they are not directly at where ligand would be, that energy level is slightly lower. What I mean by lower, we'll get to that in the next slide. But basically, when the ligand approaches the metal center, the electron on the ligand will repel the d orbital because we know there's no more than 2 electrons can occupy one orbital. Okay, so that's what we call the split patterns. So basically, for the free metal ion, we call that the d orbital energy of free metal ion are degenerate. It just means they're the same energy level as you see here. Okay? So as the ligand approach, because there's electronic repulsion, you raise the energy of your system. Okay? And depending on which orbital we're talking about, for an octahedral, okay, this is important because depending on the geometry, the effect of a ligand on the metal ion can be different. Okay, so when you in an octahedral crystal field, your ligand is directly pointing at the dz squared or dx squared minus z squared, your energy level is higher. And also we call that the E set. And then for the other 3 orbitals, they have slightly lower energy. We call that T2 set. Okay, so in inorganic chemistry, you guys will learn more in depth of where all these notation come from. But here, what you have to recognize is this splitting energy. So with this energy, this will explain the color of your coordination compound. Okay, so we already talked about this. The d orbitals are repelled by your ligand electrons. Okay, and the higher energy, we call that Eg or T2G. So G, I think here is the ground state because you also have a higher, you can also have higher energy level. So let's look at the crystal field effect. So if you flip to your page 1059, you will see weaker field and strong field depending on the structure of your ligand. Okay, so here is actually showing the energy level difference between their T2 set and the E set. Okay, so to remind you, this is what these different orbitals look like. Okay, all right, so if you look at on the far left, okay, when you have a fluoride as your ligand, it's a weaker field ligand. That's why the difference between 2 energy levels is smaller in comparison to the stronger field ligand, the cyanide group, okay? So this is that delta, okay? So we call this energy difference crystal field splitting energy. So this will explain the color and the electronic properties. So what does that mean when we absorb color? So from the previous semester, you guys learned that energy are quantized, right? So when you have the energy level suitable enough for absorbing a photon of certain energy, this can also be applied in coordination compound. So this is what you see here. This delta is for the photon with the energy of 495 nanometers, so you can use E equal to HC equation or H mu, that equation to figure out the energy of these photons, right? So when you have a longer wavelength, that means you have a weaker, lower energy photons, okay? When a compound with such a electronic configuration, when the light comes in, it basically populate or excite this electron to the next energy level. So you may wonder what will happen to this electron, okay? So because overall we want to get to the lower energy state, it can either relax in the form of heat or in the form of light. Okay, it can emit proton at the even longer wavelengths. Sometimes we call that fluorescent. And as you progress in more advanced chemistry, there are different pathways, and there's singlet and triplet state, so where you would get fluorescence and phosphorescence. Okay, so when we're looking at two different type of organization of your electrons, okay, so for the fluoride, which is the weaker field ligand, and we know the delta, the splitting energy is small, but also the way it organizes its electron will be different than the case of cobalt cyanide. Okay, so when we have lone pair at the higher energy state, we will call that high spin. And then when it's at the lower energy, we call that the low spin. And we know being able to have magnetic property, you must have lone pairs, okay? You must have unpaired electrons. So basically, why the delta change, okay? That has to do to spin pairing energy, okay? Because if you want to actually fit another electron into the same orbital, where they have two different spins, that electrostatic repulsion will increase your energy of your system, okay, as you can see here. Okay, so this will affect where this compound will absorb color, okay, of certain wavelength. Okay, so then things are a little different when we get to different kind of geometry. Previously, for the octahedral, you will see there are two scenarios, right? Now try to remove this octahedral shape, try to remove this purple color. Where you have a tetrahedral ligand orientation, you would only have one scenario where you will have orbital directly interacting with the ligand, right? With three other sides in between these lobes, in between these orbitals. So that will give you a slightly different distribution of their energy. So you will put the dxy, they will be higher energy because you are not directly pointing at where orbitals are. And for the square planar, so this is a comparison octahedral to square planar. It gets a little bit more complex. It has 4 different energy states. And that's what gives these compounds very unique electronic and optical properties. Okay, so for ligand field theory, it will also consider molecular orbital theory. Then you will get something complex like this. So here is a different metal, same metal with different ligands. Okay, so we know the iodide from the spectrochemical series. Okay, with the iodide, it's a weaker field. Okay, so your energy is lower. And as you get to the cyanide, you raise the energy level up. But then you have these multiple energy levels. So I think that's all you need to know for inorganic, okay? And if you haven't read the book, I will encourage you guys to do so. And then now we'll be talking about organic chemistry. So on the midterm, a lot of people did not recognize this word, catenation. Okay, so catenation is the ability of an element to form bond with one another. Okay, so for carbon, it's capable of forming catenation. This really has to do with the nature of carbon and its valence electron. So it's able to form bond with itself. Okay, so today, first, we'll go over a different functional group, and I think it's important that you guys recognize these functional groups, because I know you may or may not learn that in high school, but for graduate school, when you're dealing with chemical compound, the common language is still English nowadays, okay? So first we'll go through 3 types of bonding system for carbon. When you have a single bond, we call that alkane. When you have a double bond, we call it alkene. And then for triple bond, we call it alkyne. Okay, so the hybridization of these structures are all different. Okay, so for organic chemistry, a lot of time we will omit hydrogen for clarity. Otherwise, you will be drawing a lot of H everywhere. Okay, so a lot of time you will see people draw structure like this. They do not have any heteroatom. You will assume there's hydrogen here. Okay, so here we know this adopt tetrahedral geometry. So it's what kind of hybridization that is? sp3, right? Okay, so for alkene, because you need to share electron here to form that extra bond, it's sp2. Okay. Then obviously this will be sp. So one important thing is you have to recognize for sp hybridization, this should be linear. Okay, so in the literature, you will see a lot of people drawing their alkyne. Okay, so in a lot of literature, people messed up and they continue to replicate their arrow. They will draw alkyne like this. That's not right, okay? It has to be straight, okay? Because it's a sp hybridization at this carbon. And at this carbon, okay? All right, so you remember A, E, when you see E, that's in double bond. And then when we see alkyne, that a triple bond, so Y. So in next lecture, we'll go into naming of these compounds. So these will tell you where these unsaturations are. Okay, so another important thing to recognize this is, okay, so I'm gonna put hydrogen around it. So this structure is CnH2n plus 2, right? So you have 6 hydrogen, okay? For this structure, it becomes CnH2n, right? Because you have 1 degree of unsaturation. That's what we call 1 degree of unsaturation. Okay, so obviously for this one, the math add up, right? So from the C to H ratio, we can guess how many degrees of unsaturation you could have, okay? Because in this scenario, you can't really form 2 double bonds, right? You only have 2 carbon. However, in some rare cases, so a lot of times you will see R group, that means just other stuff. Okay, so in rare cases, you can get a structure like this. We call it allene. Okay, and then this is very reactive. We'll talk about it in the next lecture. So it's possible to get a structure like this for a 3-carbon system. If we count the electron, okay, so again, you have 4 hydrogen here and 3 carbon, right? So it had 2 degrees of unsaturation. So assuming these R are H, we get a C3H4 system. Okay, so that is correspond to this, right? That makes sense? Okay, so when you, by counting the C to H ratio, we can guess to some degree what the structure might be. And let's talk about another special case. So let's look at alkene. It has a CnH2n ratio, right? Okay, so let's talk about a cyclopropane. Okay, we call it 3, it's propane. Okay, so cyclopropane, it has what? 2 hydrogen on each of these 2 points. When you have a ring, it can also cause your C to H ratio to change. Okay, so when you see this ratio, necessarily means it's 1 degree of unsaturation. It can also adopt a cyclic structure. And in some cases, you can have multiple these cyclic ring on the same molecule. So having talked about alkane, alkyne, now we'll go into more complicated names. Let's talk about, this is alcohol. So it's exactly the way it's read, aldehyde, okay? So this Y pronounced similar to the I here, okay? That's why we call it alkyne. We pronounce it as I, okay? So aldehyde, okay? And then you have carboxylic acid. Okay, so how are these different? You can see here you have single bond, right? And for aldehyde, you have double bond on the oxygen. And then for acid, you have one extra atom, right? So we call this oxidation. We can oxidize alcohol to form aldehyde, and we can oxidize aldehyde to form carboxylic acid. And aldehyde has a cousin called ketones. Okay, so what are ketones? So when you do not have the H, then we call it ketone. Okay, both sides, these are carbon, and other stuff. Okay, so the way I memorize, when you think of ketone, when you see O-N-E, you automatically think of this type of structure. And sometimes this functionality, C double bond O, we also refer that to carbonyl group. So when we are describing the organic chemical reaction, you must refer to the correct name, at which position reaction occurs. Okay, so in organic chemistry, it's all about the transformation between different functional groups and how you can connect different functional groups together. Okay, so for instance, we can connect these two together, then we will form ester. Okay, so these are the fruity smell that you smell for the fruit, a lot of ester. Okay, and then it has its cousin, which would be amide. Because when it reacts with amine, when the carboxylic acid reacts with amine, it will form amide. And this is not the only case. Okay, you can also have another substitution on this nitrogen. We will have primary amide, which means you only have NH2. And secondary amide, you have an R group, and tertiary amide. So tertiary, that means 3, okay? So depending on the amount of substitution on this amine, this will be different, okay? So one characteristic of amide is capable of forming hydrogen bonding with another amide. And that hydrogen bonding is what's responsible for some material. They have very good mechanical properties. So you think about nylon, okay? So this is the primary building block in nylon, or Kevlar, which is an aromatic amide. This is the overview of common functional group, and I think there's a few that hasn't been mentioned yet, where you will have, of course, amine. So again, we will call this a primary amine. It only has one substitution. If you have an NR2H structure where you replace one H with another carbon, we call it secondary amine. And then for trimethyl or triethylamine, we call that a tertiary amine. And in some cases, you can even get a quaternary amine, which you also refer as ammonium. Okay, remember ammonia and ammonium hydroxide? Ammonium. All right, so when you combine amine with carboxylic acid, that gives you amide. Okay, so for amine, we can also have a different structure where we call it nitrile. And this group in inorganic chemistry, we refer it as cyanyl group, right? So, or cyanide. Okay, so when you connect to a carbon, we call it a nitrile group. And for chemical transformation, you can deal with it. So what we can do is, this is a group where we can, after we hydrolyze it, after we react it with water, with excessive amount of water, potentially you can generate carboxylic acid from this structure. So look, the carbon is sharing these electrons with nitrogen, right? So if we think about the Lewis dot structure, the 4 valence electron on carbon is shared between its neighboring carbon and 3 with the nitrogen, right? If we hydrolyze it, it will give you carboxylic acid, where the central carbon, that C, is located here, is sharing electrons, 2 here with the oxygen, and one on each side. And this is why we have to teach you guys Lewis structure at first. You will see these concepts will keep coming back over and over. So now I want to bring your attention to page 55. Okay, so here are a list of different organic functional group that's commonly observed. And it also have its Lewis structure to show you where are lone pairs. And there are ball stick model that just give you a sense of what it looked like. Tetrahedral structure, these things are three-dimensional. So another thing is we can also replace hydrogen with halogen. So we call the halocarbon, okay? Halo comes from its halogen. Alcohol can also react with halogen, where its lone pair can undergo substitution reaction and give you structure like this, where we call this ether. Depending on the structure, okay, you will go into the reaction mechanism. So if you think about reaction intermediate for, I think in the earlier chapter where we talk about intermediate species in a chemical reaction, okay, so we're talking about gas molecule colliding with each other and forming this intermediate structure where you have essentially 5 bonds, but not 5 real bonds, okay? Carbon can only form 4 bonds. It's impossible to have 5 bonds. Okay, so depending on the structure of here, whether it is a primary, secondary, or tertiary, that means how many substituents you have around that carbon, you have 2 different reaction mechanisms. But for now, we know at the end of reaction, you can form ether. Okay, so that's a substitution reaction. Okay, I think that's most of functional group that you guys will encounter. Okay, so we will talk about addition and elimination reaction. So let's go back to this double bond, okay? In the presence of catalysts, usually inorganic catalysts such as palladium, you go from ethylene to ethane. Okay, so in the presence of such as palladium catalysts and other inorganic metal can also do this. It can help the insertion of hydrogen across the double bond. So that's called hydrogenation. And then this is commonly used, for example, for the oil. If you want your cooking oil doesn't go bad, usually we will use hydrogenated vegetable oil. So that means it removes the double bond from a fatty acid. Okay? We can also do elimination reaction to go backward. Okay? But of course, if you have to think about the thermodynamics, you need to put in a lot of energy to rip off these CH bond, right? And then reform this double bond. Okay, so generally, if you look at your book, for the elimination reaction, it uses X and Y to describe different kind of leaving group or different kind of substituent. You can do elimination reaction and give you double bond. So one very common elimination reaction would be, so this would be a real example. Let's say you have an ethyl bromide, right? In the presence base, so one important thing in inorganic chemistry, it's all about the electron flow. Know where the electrons are going. So you can actually think of different reaction mechanisms. Some people just don't get it, but with practice, organic chemistry is like its own language. Okay, so this base can come in to take away that proton because we know this, when it take away a proton is H+, right? So where did that extra electron go? There's a lone pair here, right? And we give it a negative charge. This can come down. And you will see arrow like this. That means the electron are moving down, giving you the alkene, while kicking out this bromo group. And what happened to the bromo group? It become bromide. Because if you think about this bonding, okay? because carbon can only form 4 bonds, okay? So it has to get rid of these electrons. It doesn't want that electron there. So you end up with a bromide here, okay? That makes sense? Okay, so this is elimination reactions, but in the case that for ethyl bromide, generally it has to do with the structure of your base. So for a very bulky base, that means you have a lot of bulky substituent around it. One example is terbutoxide. If you have to draw the ball stick model, you can think of this as a very bulky phase. So elimination is preferred. But when we have a less hindered base, such as methoxide, what could happen? When we have a less bulky base, it can also attack this carbon, undergo substitution reaction. And depending on the nature of your base, in this case, you will generate ether as your side product, okay? If this base is an hydroxide, when you're doing this reaction, both reaction mechanism is feasible. You really have to look at the activation energy and the heat of reaction. So there will be competing reaction. When we treat ethyl bromide with hydroxide, you will generate both ethylene and ethanol, ethyl alcohol, because you're kicking this bromide out and generating alcohol. So when you're designing chemical experiment, you really have to think of what is the dominating mechanism and what is the preferred product. Is there any way we can change the reaction preference? Then you have to think about Gibbs-free energy. Is that endothermic or is that exothermic reaction? Okay, depending on the activation energy of different mechanism, you can control the probability of which pathway it will adopt. If you have your book, I want you guys to look at page 651. Okay, so again, heated reaction. Why do we need to learn about Hess law and heated reaction, bond formation energy? Okay, this is where it takes place. So heated reaction is basically the net energy of bond forming and bond breaking processes. And as you can see here, where we add, so here we can add high hydrogen across the double bond. You can also add strong acids such as Cl, HBr, and HI across the double bond. And in this case, if you do the math, we can see these reactions are generally exothermic. It generates excess amount of heat. That's why we need to know about the energetic of your reactant and your final product, and that will determine whether this reaction is endothermic or exothermic. From the delta G equal to delta H minus T times the delta S, we can also determine whether these reactions would be energetically favorable or thermodynamic feasible or not. So I think we covered a lot of it for now, and in the next lecture we will start talking about different aspects of organic chemistry. Any questions?